So this was also the start of me experiencing a real world problem in terms of data centers. But still, it's very research oriented. So I was exposed to a new project. This was a European consortium project. So you have on the bottom here, I've listed a bunch of different people like IBM, Atos, Acciona, and some universities as well there in that list. So I was working for United Technologies, but I was in this consortium together working on this research oriented project funded by the European Union. So the idea is to do like a next generation data center, which is highly efficient in terms of energy, not efficient in only one place, but efficient in holistically with the entire data center in mind. So typically what happens in data centers, if you've seen one, the picture on the top is kind of an explanation of that. You all you see is just like open floor with a lot of racks and servers lined up in it, right? This is how it typically looks like. But behind the scenes is like there's a heating and cooling system that ensures the right temperature is set inside the data center, and also the power supply that comes to those, to both the heating systems, cooling systems, as well as the IT devices itself, which are the servers. Essentially, I mean, you have your email client on Gmail. You have no idea physically where it lives, right? Like it's you go google.com, you see that, right? But then it physically has to live somewhere, and that all happens in the data centers, right? And that kind of naturally made me very inquisitive to learn more about this field, and that's why I got into this by myself. So in here, this research oriented project, the goal was pretty hard in the sense, what you see on the rightmost tab is the set of goals that was supposed to be achieved in this project. And this was also a project where you could demonstrate stuff. So we had a couple of test bed data centers where we were testing out how this works, and to demonstrate that we could do energy saving on this, right? So the goal was to use renewables as much as 80% to power all of your equipments, which is quite hard. It doesn't as of now happen anywhere in the world to my knowledge. But this is, like I said, it's a very research oriented project. So there are a lot of factors that has to be weighed in, but the goal was to achieve 80% renewable usage, be it solar, wind, or batteries. A combination of all of them, and then to also reduce the energy total DC data center energy consumption by 25%. And there are other goals as well related with emissions. Essentially what's happening is, the way I view the data center is there are like three different pillars. The one that's on the IT side is where you have the servers, you have your application that's running, and you don't want the power to go away at any cost for them, right? Otherwise, your Gmail is down, you can't get a ride on Uber because the data center is down, right? Then B is the cooling side, the cooling pillar, where the cooling pillar ensures that the internal temperature within the data center is maintained at a given set point. Then C is your power consumption, where you provide the power supply to both the IT pillar and the cooling pillar. At this point of time, there are optimization that is happening everywhere across the board, but there is no one place which does an optimization of all three in a coordinated fashion. And that was the goal of this project. To on the left picture that it shows, the supervision or the supervisory intelligence is supposed to be like a component that essentially coordinates the control decisions across the three pillars. And I was instrumental in devising that, and others had their own share in developing the other components. This was a very nice experience for me, and this kind of kept me going, that I wanted to keep pursuing the data center world, to see, because there's so much scope for things here. Because going forward, when the internet of technologies come in, or anything new that comes up, you're going to have a lot of data, period, right? And then all these data have to live somewhere, and data science is the way to go forward for that, as well as data centers is a place where those data is going to reside at some point. So I felt this is the thing to go after, and I kept going on this line of things. So moving on to the next slide. I worked with a Silicon Valley startup here, which dealt with managing power within data centers. So essentially, we are looking at a problem where we were specifically kind of boxing ourselves within the IT domain and looking at the power infrastructure for the data center. So the picture below shows a very simplified representation of that. Imagine there are two feeds of electricity coming into your data center, A and B, and there are usually UPSs which will back you up that even if the feed goes down, it has sufficient juice in it for at least 15 minutes to keep the data center running without failing, right? And then imagine there are four racks below them, and each one of these racks draw power from both sides, that is both A feed as well as B feed. And all data centers are usually built like this, that they have a lot of redundancy in them, and as a startup we were trying to make use of that redundancy in some way. So can you move on to the next slide, Oz? So if you see what happens, let's imagine this scenario where, let's say, the UPS is built for withstanding 100 kilowatt of capacity. So you can imagine all these racks, R1, R2, R3, R4, contain servers in them which draw at most about 25 kilowatt power per rack, right? So typically what happens is when both the feeds are powered on, you would be consuming equal power on both feeds, so 50 kilowatts on feed A and 50 on feed B, assuming every rack is actually consuming 25 kilowatt, right? So you don't want to add more capacity than this, because the reason being, if for any reason one of the feed is lost, and assuming the UPS also goes down, which is occasional, it doesn't happen too often, maybe once a year or maybe twice a year for no more than a few hours, or like it should be within an hour at most, right? And it does happen. So at that time, even during that time, your one of the feed is fully loaded and it doesn't let the racks die. That's the whole point of having building that redundancy, so that you ensure that the racks are always powered. So even if the data center comes down, your Uber app, you could still order a ride and your Gmail won't go down. That's the whole point of that, right? You want to keep those applications running no matter what happens. But then if you click one more slide, Oz. So typically what happens is, as a product within the startup, what we were trying to facilitate to this environment is to reuse that redundancy. We are aware that, hey, your feeds don't come off. You can actually put more power and eat more power in that. It's possible. So we were saying that, why can't you add two more racks with the same 25 kilowatt? Yes, now your individual UPSs are going to go up to 75 kilowatt, which is still okay because you have 100 kilowatt capacity on them. But for whatever reason, something has to happen, and say the one of the feed goes down. Then we ensured that those new racks that we added, they come off immediately so that they don't consume that extra power. So it's essentially you're saying, hey, I want to run some workloads which I really don't care if they're running 24/7, 365 days. I'm okay to take a hit on them for a couple of hours in a year. Then can I not do that? So we are facilitating that. Um, but then can you move forward one more step, Oz? So, but in reality, these racks never actually consume 25 kilowatt of power. This is just what we imagine in our heads, and say the data center operator has in his mind that, okay, I'm going to load them up with as many servers in each rack to consume up to a 25 kilowatt and no more. But if you actually see, this is like a time series power consumption, and that never goes to 25 kilowatt. It does rarely, but the peaks never line up. Only if the peaks actually line up, you will have that problem of, hey, my data center is fully loaded now. But that never happens. That's what we've seen in reality in several places. So what we did is, like, why should we have that assumption that, hey, I know this rack is allocated or configured for about 25 kilowatt. Instead, we throw away that assumption and go look at the actual power consumption, which could get tricky because, if you lose power for whatever reason, your data center is in trouble. So you don't want that. So in order to avoid that, what we did is we said, instead of using actual power, why can't we use some kind of a prediction? So we use machine learning to enable power prediction, which is just a time series data. So looking into the future, you make decisions ahead of time so that you avoid any catastrophic scenarios. Move forward, Oz. So we weighed in what can we do. So we could obviously use machine learning is very well tuned for this. You could um, easily predict future to a certain level of guarantee or uh, so we said, okay, for every 10 seconds we make a prediction, and then we assume that the racks would not consume more than that. And we said, well, maybe for at least it should be valid for the next future 20 seconds. That was our assumption. And we could use any simple regression technique for doing with the time series data for this. And we did use just gut feeling says use the average power from last 10 seconds to predict the future power in the next 20 seconds. But the question is that good enough? Not necessarily, because you never know, the power consumption might suddenly jump up high. So in order to be safe, we said, instead of calculating the actual power consumption and using just going by the mean value, we used like a statistical way of saying, why can't we predict the 99th percentile um, of the power consumption, so that ahead of time we know if power consumption is going to go up, the 99th percentile, calculating that would catch up faster than calculating an average, because that might still be on the lower end. So we said, well, you could just use a simple standard linear regression for this, but instead, because we are calculating a percentile, we use a quantile regression. And essentially, it kind of draws a line through the data. You'll see a picture of that in the next slide. Also, if you don't mind moving to the next slide. So essentially, at every snapshot of time, so this is just a picture on the left, is a very academic example, like a hand wavy picture you see on the left. Imagine you want to predict the future 20 seconds power consumption, and on the right side is the picture where you're taking a look at, through statistical ways, over time, for every 10 seconds you calculate the average power consumption within that window of 10 seconds, and you will have 10 points for that, obviously, right? And then for those 10 points, that will actually give you the future power consumption, which is just one value. So that's why you see there are three different time slices, T1, T2, T3, and at each of those time, the average power consumption is just single value, but the future power consumption is what is plotted on the left, on the y-axis. So you see multiple points are on the same points. So essentially what it is if you want to calculate the 99th percentile, you just simply draw a line. So you a straight line that avoids only 1% of the total number of points above the line and consumes 99% of all the points under the line. That's the line that you're looking for. Move on to the next slide. So what kind of data did we have? This is like the sensor data time series. That is, at each time step, for us, we went as granular as half a second, and for every half a second, we went to the power meters and, hey, give me the power, give me the power, and we kept polling, and we have all the time series data. Now, the data can explode very easily. If we are, say, doing this not on the toy example of 5 or 6 racks that I shown, but on 500 racks, then we could easily run up to tens of gigabytes per day. So that was the data that we had, and we ran our predictions with that data set. And move on to the next slide. And how well did we do? We did pretty well, actually. So if you look at it, the blue line is what we predicted, and the red line is what actually happened. And we are actually calculating the actual max here. So we're kind of saying the blue line is on top of the actual maximum. It is possible that we may not always be accurate, because keep in mind, we were trying to estimate the 99th percentile and not the absolute maximum, right?